You ever wonder why Miss Universe has always been won by a girl from Earth? I think there's some bias in that competition. I don't know. I don't know what you think. Hey, chime in. Tell me what you think about that, because I don't think that's fair. I mean, I like the home team and all, but you know. Anyways, we are talking about the fourth lesson in thermodynamics, which is Gibbs free energy. Gibbs free energy. So let's talk about that. In 1878, so in the late 1800s, Willard Gibbs, a physicist at Yale University, defined a combined enthalpy and entropy function called Gibbs free energy, and that's going to be represented with a capital G. So it's a function of both enthalpy and entropy. Gibbs free energy is used to determine if a reaction is spontaneous or not. So this combination of entropy and enthalpy together will help us determine if a reaction would actually happen or not. Because sometimes you put things together and nothing happens, and sometimes you put things together and something does happen. So how do we know? Well, Gibbs free energy calculations help us determine that. The formula for Gibbs free energy is that the change in free energy of a system is equal to the change in enthalpy of the system, which remember that is the change in heat energy, minus the temperature times the change in entropy of the system. What's very, very important to note and remember is that the temperature must be in Kelvin. It must be in Kelvin. And let's think about this. Remember, delta S is entropy, which is disorder. So as we, and look, it's a function of temperature. As we decrease the temperature, the disorder gets less because we're multiplying it. Because why? As we decrease the temperature, things move slower. And if things went as cold as possible, which is absolute zero Kelvin, remember Kelvin has no negative values, then you would have, and there would be no disorder because 0 times whatever the change in entropy is 0. So if it's 0 Kelvin, there is no disorder because there's nothing's moving anymore. So that's why it has to be in Kelvin, because we can have 0 Fahrenheit, and there's certainly disorder there. We can have 0 Celsius, and there's disorder there. So we have to have it in Kelvin. And what makes even things worse is you can have negative Fahrenheit and negative Celsius, and we wouldn't want to do that. So temperature will always be a positive number. So that's going to be very helpful to remember when you have to do some predictions with this. So the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. What this means here is, doing all this, if you get a negative value for Gibbs free energy, then that means this is a spontaneous reaction. So if energy is given off, this is a spontaneous reaction. If it's positive, that means it requires energy. If it requires energy for this reaction to occur, that would be a non-spontaneous event. That means you have to give it energy. That's not spontaneous. Things will spontaneously, like the sandcastle, will spontaneously fall apart on the beach, but forming it, you would have to add energy to it. That's not spontaneous. So I've got 4 examples here, and let's analyze these with these signs and determine if they are spontaneous or non-spontaneous processes. So in the first one, if I have negative delta H, which by the way, that means it's exothermic, it's releasing heat. So I've got an exothermic reaction, so it's a negative value here, minus, remember temperature will never be negative, so let's not worry about temperature. So negative minus a positive delta S, that means it's more entropy. Positive at delta S, we're increasing the disorder. So negative minus a positive is becoming more negative, such as negative 10 minus, we'll say positive 10, negative 10 minus 10 would be negative 20. So no matter what numbers I put in here, a negative here and a positive here, it's a negative minus a number, it's always going to be negative. So in this situation here, for an exothermic reaction that is increasing its entropy, this will always be spontaneous. This is always spontaneous. Let's take a look here. We are still increasing entropy, but in this situation here, we have an endothermic reaction. This reaction here is increasing, it's it's adding heat to it. So we're getting more disordered, but we're adding heat to that. So let's put some values here. So I have a positive minus a positive. So if I had 10 minus 10, well, that's 0. What if I change this to 20? 20 minus 10, that's positive 10. So that would be non-spontaneous. But let's change this here. What if I said 10 minus 20? 10 minus 20 is negative 10. So that would be spontaneous. So it really depends on what number I put in here, doesn't it? So this spontaneity depends on the temperature. So sometimes this can be spontaneous and sometimes it won't be spontaneous. This all depends on the temperature of the system. So this number here will affect our enthalpy, our entropy. So this temperature will affect this number, making it larger or smaller, which will affect this reaction here. Let's take a look at the third example. We have exothermic in the third example and less disorder. So we're becoming more ordered and it's exothermic. Let's put in some values here. A negative, because this is negative in this box, so let's say negative 10 minus a negative. So negative 10 minus, we'll say negative 10. That would be the same as saying negative 10 minus a negative, by the way, is adding something. So negative here, that would be the same as saying negative plus something. So negative 10 plus 10 is 0. So we kind of have the same problem we had over here. If I have a larger number here, negative 20 minus 10 would be negative 10. But if I put a larger number here, negative 10 minus 20 negative 10 plus 20, because a negative and negative, would be positive. So in this situation here, I have another problem here where it's just going to depend on the temperature, the spontaneity. So just because it's exothermic and less disorder, we can't really draw a conclusion. Let's look at the fourth box. We have an endothermic reaction that is becoming less disordered. So I'll put a positive number here and put a negative number here. So positive minus a negative is the same as saying positive plus something. So whatever numbers I put in here, let's say 10. 10 minus, that has to be negative 10. So 10 minus negative 10 would be the same as saying 10 plus 10, which is positive. No matter what numbers I put in here, this is always going to be a positive number. This will always be non-spontaneous. So endothermic reactions that have a negative change to entropy will never be spontaneous. We're going to explore this. Let me give you some examples right now. Okay, so here's our equation. Free energy equals change in enthalpy minus temperature times change in entropy. In the first situation I gave you before, we said that if it's getting increased entropy and decreasing in enthalpy, releasing heat, a negative change to enthalpy, we said it was always spontaneous. Okay, if I put a positive number here and a negative number here, negative minus a number is going to be more negative always. So this, at all temperatures, this is always going to be spontaneous. In the second example, we said that it was sometimes. So let's analyze this a little bit more. So if I put in a positive number here and then I minus another positive number, it really, it depends on how big the temperature is, because they say, if I have a positive number here and a positive number here, temperature is really going to affect this. So at high temperatures, this will be spontaneous. So let's think about this. If I put a number here and another positive number here, the higher the temperature, the bigger this part of the problem gets. So at high temperatures, the more spontaneous this gets. Let's give an example of that. So if it's increasing in entropy, that means it's becoming more disordered. Such as if I take water and I turn it into water vapor, if water evaporates. So water evaporating, remember, a liquid becoming a gas, that would be a good example of increase in entropy. water becoming a gas. In that same situation for the enthalpy here, for water to become a gas, water needs to gain heat, gain energy. When you add energy to a system, that's endothermic. The system's gaining energy. So when water becomes a gas, that is also an endothermic process. It's gaining energy and it's becoming more disordered. Water becoming a gas, water evaporating. Does water spontaneously evaporate? Well, it depends on the temperature. At high temperatures, water evaporates. At low temperatures, water does not evaporate. So because of this, we say that this is entropy driven, because the entropy is really what's driving this reaction. This reaction, it wants to become more disordered. It's going to, having a positive number for entropy, remember you're subtracting that, so having a positive number for entropy is going to increase the spontaneity of this. Having a positive number for enthalpy is not. Things want to give off heat. They want to burn. They want to fall apart. That's what's natural. Absorbing heat and becoming more organized is counteractive to spontaneity. So this is why we call it entropy driven, because the disorder is what's driving the water to become gas. It's because it's becoming more disordered, and that's what's driving it. But it has to happen at high temperatures because it has to have energy added to it. Let's look at this one here. A negative change to entropy, so it's becoming more ordered, it's less disordered. That's what negative entropy means. It means it's becoming less disordered. And a negative change to enthalpy. In other words, the enthalpy is, the heat is releasing heat. So this is an exothermic reaction that is becoming more ordered. And I'll give you an example of that. We're using water again. We'll go the opposite way. So instead of water becoming steam, let's talk about water becoming ice. So when water becomes ice, the entropy, water becoming ice, this is less disordered. Ice is more ordered than water, or in terms of entropy, it's less entropy, it's less disordered. Ice has less disorder than water. Let's look at the enthalpy here. In order for water to become ice, water has to lose heat. The heat has to leave the water, and then it will become ice. So this happens spontaneously at low temperatures. Water will spontaneously become ice at low temperatures. And if we think about that, we have a negative value here, which is going to help make delta G negative. But if I have a negative value here for enthalpy, that doesn't help, because remember, we're minusing a negative. So what's really driving this one is the enthalpy. This is enthalpy driven. The fact that water becoming ice, giving off heat, things want to give off heat. They want to burn, they want to break down, they want to decompose. They're going to give off that heat, and that's what's driving this reaction for water to become ice. It's not driven by the fact that water is becoming more ordered. That losing entropy is not going to help in spontaneity. In our last example, we say, okay, we've got a situation where we're becoming less disordered, and we are also endothermic. So it's adding energy and it's less disordered. And we said that this is not spontaneous. It's not spontaneous at any temperature, because we have a negative value here, and then we're minusing more from it. It's already negative. I'm sorry, positive. So we have a positive value for enthalpy, and then we're minusing a negative, so we're adding to it. So we already have a positive value, and then we're going to add more to it. It's already positive, and it's making it more positive in this situation. So temperature, it doesn't matter what the temperature is, this is never going to be spontaneous. However, the reverse is spontaneous. So if one direction is non-spontaneous, then opposite of that reaction is spontaneous. So the opposite of this situation here is this situation. Less disorder, more disorder, endothermic, exothermic, non-spontaneous, spontaneous. Just like these two are opposites of each other. Water becoming steam, and this could be said as steam or becoming water, condensation. So it's just the reverse is true. I know that's confusing. Pause the video, take notes, think about this again. It's very conceptual. It's very conceptual. All right. So if the law of the universe is saying that it's becoming more disordered and things are spontaneous, why would a non-spontaneous reaction happen at all? In other words, many chemical reactions that enable plants and animals to live and grow are non-spontaneous. That is, the delta G of the system is positive. How does this happen? Well, in living systems, non-spontaneous reactions often occur in conjunction with other reactions that are spontaneous. So having this order, how does this happen? How do we have these processes? And it's driven by other reactions that are spontaneous. So you have several spontaneous reactions that can make a non-spontaneous event occur, such as burning gasoline. We know that's a spontaneous reaction. If we have gasoline and oxygen and we add a spark to it, it burns. And if you have enough surface area, it'll blow up. That's a spontaneous reaction. Let's think about a car at the bottom of a hill. If you have a car at the bottom of a hill, it doesn't spontaneously go up the hill. It's going to sit at the bottom of the hill. However, we see cars going up hills all the time. How is that possible? Well, what I just said was burning gasoline is spontaneous. And that spontaneous event of the gasoline burning, if it just burned out in the atmosphere, it would be over. But what happens is we trap that energy in the car engine. So when it burns up, when that gasoline burns up, it throws a piston down. So that energy is being used to throw a piston down. And that piston moves back and forth as it goes up and down, and it turns an axle, which turns your wheels. So the spontaneous event creates the spontaneous event creates a non-spontaneous event where a car goes up a hill. And this is what coupled reactions are all about. It's about spontaneous reactions driving the energy from spontaneous reactions driving a non-spontaneous process. So this is known as coupled reactions. Free energy released by one or more spontaneous reactions is used to drive a non-spontaneous reaction. For instance, if you have energy in carbon dioxide and water, let's think about that. Let's add energy. So I'll make some water. I got water. I get it hot, adding energy to it, and add carbon dioxide to it. I'll blow on it. I exhale carbon dioxide. So if I blow on hot water, will it make sugar? Then I think we all know that ain't going to happen. I can blow on hot water all day long, but it's not going to make sugar. But this is what plants do all the time. This reaction here is photosynthesis. And you don't have to memorize this for my class, but if you take AP biology or even general biology, a lot of teachers will make you learn this process because this really is the most important chemical reaction for life. All these red arrows in this process, by the way, this is a process that happens in plants, photosynthesis, in a particular organelle in plant cells called chloroplasts. They're what make plants green. So where you see green on plants, this is going on. And every one of these arrows is a different spontaneous reaction. But part of that energy from these spontaneous reactions add to energy to make another reaction occur. So energy from the sun and carbon dioxide and water, piece by piece, a hydrogen gets added here, gets removed there, carbon gets added, and piece by piece by piece, this is built. This is not built at one step. As we learned in kinetics, there's a lot of intermediate steps going on here. There's a lot of reaction mechanisms. So there's a whole lot of spontaneous reactions that make a non-spontaneous event occur. And that's all I need you to know about coupled reactions. All right, so let's do an example here with some actual values. So for a process here where the change in enthalpy is 145 kilojoules and the change in entropy is 322 joules per Kelvin, is the process spontaneous at 382 Kelvin? When I ask questions like this, I want you to show your work and I want you to solve for G. You got to solve for G to figure out if something's spontaneous or not. So, but before we get to that point, let's just take a look at this question and pull out information. So I'm not reading a question, rather that I am now looking at some values in a question. So as we pull it out, we know our change in enthalpy, we know our change in entropy, we know our temperature, which our temperature has to be in Kelvin, so this is nice. Remember, if it's not in Kelvin, we have to add 273 to Celsius to make it Kelvin. And we are solving for our change in free energy, Gibbs free energy. When I look at this here, when I look at it this way, something kind of jumps out at me as a problem, something that we're going to have to deal with, and that is the fact that enthalpy is in kilojoules, but entropy is in joules per Kelvin. And kilojoules and joules kind of don't, we're going to have to convert something here. Besides that, we also need to know how do we solve for delta G, so we're going to have to remember our formula for free energy, and this is what my setup would look like. So we're going to first have to convert kilojoules to joules, and that's something we should notice if we do step 1. And there's 1,000 joules per 1 kilojoule. So using dimensional analysis, I take 145 kilojoules. Kilojoules cancel each other, and I have 145,000 joules. So basically, to convert kilojoules to joules, move the decimal place to the right 3 times. Our formula for delta G, or free energy, is free energy equals enthalpy minus the temperature, which is in Kelvin, times the entropy. So let's plug in the values here. That's what we need. Number 2 is equations and conversions. Number 3 is plug it all in. So I'm plugging in my enthalpy here, which is in joules, subtracting my temperature times my entropy. And since entropy is in joules per Kelvin, the kelvins will cancel out. A Kelvin times a joule per Kelvin. The kelvins cancel each other out because you have a numerator and a denominator. And now we have, we multiply these two together, I got 123,000 joules. So 143,000 joules minus 123,000 joules comes up to 22,000 joules. Now, because this is a positive number, this is non-spontaneous, meaning we would have to put energy into this system for this, whatever reaction it is, to occur. So let's take a look at some practice problems. Now, I have got 4 practice problems, just as this is the first set that I want you guys to do. So I want you to pause the video twice. Once on this one, and then once you finish this, this is the second set of questions. So pause the video here as well and try to answer these. Remember, these questions are essay questions, so you should write complete sentences that reiterate the question, that really explain that you understand something. In other words, don't just say entropy is increasing. You should say something to the effect that entropy is a measure of disorder, and you can see that the disorder is increasing in this example. So you got to be very clear when I ask you to do essay questions. And I do that because the clearer you are, the more you're going to have to dig and really understand what's going on here. And that's my method to my madness here. So pause the video on those 2 spots and then restart it when you want to look at some answers. So pause now. Okay, you should have paused and answered these questions by now. So let's take a look at the answers to these questions here. So in this situation here, we are just plugging in values into our equation here. So let's take a look at our setup here. So for 1A, put this in here. So 1A, we have, remember that it's free energy equals enthalpy minus temperature entropy. So for 1A, we have the enthalpy. Remember, we got to move the decimal place over 3 times because it's in kilojoules. It gave it to us in kilojoules, so I'm going to convert this right into joules. So it's negative 75900 joules. That's our enthalpy. I had to convert the kilojoules to joules by multiplying by 1,000. And that is going to be I'm going to subtract that from 273 Kelvin times our entropy, which is 138 joules per Kelvin. We see that Kelvin cancels with Kelvin. So let's take care of this first, this part here first. So I'm going to say that we have 273 times 138 That is, so this would say delta G equals negative 75900 joules minus 37,674 joules. And so we can plug that into our calculator. So I have 75900, and remember that's a negative value here, and we're going to subtract 37,674, and so I have a delta G equals negative 113,574 joules, and since this is negative, this would be spontaneous. That's a spontaneous reaction because it's negative. Okay? Alrighty. Let's try number 2. Or 1B, I should say. 1B. 1B, remember, same thing. The change in free energy equals the change in enthalpy minus temperature times the change in entropy. So the change in free energy equals, in this case, we have negative 27,600 joules minus, our temperature is 535 Kelvin times negative 5.2 joules per Kelvin. Same setup as last time. Cancel out my kelvins. So let's try this. 535 times 55.2, and that's a negative number. So now we've got our change in free energy is negative 27,600 joules minus negative 29,532 joules, which is a negative minus a negative is positive, but I'll just plug it in the way it is says on my paper. So we have 27600 negative minus 29532, which is also negative, and we come up with the change in free energy is positive 1,932 joules. The fact that it's positive means that this is a non-spontaneous reaction. That means this process would require energy. This one would require energy. It wouldn't be spontaneous. Alrighty. Our next one, 1C. 1C. Free energy equals enthalpy minus temperature change in entropy. Our free energy equals, in this situation, our enthalpy would be 365,000 joules minus 388 Kelvin times negative 55.2 joules per Kelvin. Kelvins cancel. Let's try that. 388 times 55.2, which is negative, and I've got an answer of delta G now is 365,000 joules minus negative 21,417.6 joules. Subtract those two. Remember subtracting a negative, so that's 365,000 minus, so subtracting a negative, it should get bigger because that's like adding 471.6, which is negative, equals. So I have a change in free energy of positive 386, 417.6 joules because it's positive. This is non-spontaneous. So this one again requires energy for this to happen. So that's our answers to the first three, A, B, C. Number 2, in terms of energy, explain the difference between spontaneous and non-spontaneous reactions. We might have heard me say it quite a bit while I was working out number 1. In terms of energy, a spontaneous reaction releases energy, whereas a non-spontaneous reaction requires energy. Non-spontaneous reactions require energy to go forward, and spontaneous reactions release energy to go forward. So that would be the appropriate wording for number 2. Okay, let's look at number 3 now. If a system becomes more disordered during a process, how does the system's entropy change? I suggest you change the words disordered with the word entropy, because entropy is disorder. So if you do that, let's read the question again. If a system becomes more disordered, that's the same as saying if a system becomes, or more, if a system gains entropy. So if a system becomes more disordered, it is gaining entropy. So how is the entropy change? It's increasing. So if a system becomes more disordered, the entropy is increasing. Okay, these questions here, I am not going to give you the answers directly, but I'm going to give you very, very, very good hints on to see if you're on the right track or not. So hopefully you gave this a try already. And I'm going to give you hints to make sure that you understand what we're doing here and that you got the right answers, that you're on the right track. So in the first one here, we've got this reaction. 2 moles of hydrogen and a mole of oxygen is producing 2 moles of water. Predict the sign of entropy for this reaction and explain. You must explain these, guys. You must. I will not give credit if you don't. So we're looking at the sign of entropy. So we're talking about disorder. We're talking about disorder here. Is this becoming more or less disordered? And you would need to review workshop 3 or lesson 3 in thermodynamics to talk about entropy changes. But what's important here is you should be really focused on the states of matter to answer this question. You should be really focused on the states of matter to answer this question properly. And that is that you have gases becoming a liquid. That's the key to A. B says, you know what, hey, how would the value of entropy for the reaction change if the product of the reaction was water instead, water gas instead? So this is saying, is in A, I was talking about this, it was a phase change kind of an issue. In the second one, I've got gases becoming gases. I got hydrogen, 2 moles of hydrogen gas and a mole of oxygen gas becoming 2 moles of water, but as a gas. So the same reason's not going to work in A as it is going to be in B. So to figure out this one here, make sure you look back in your notes on how does entropy work when gases turn into gases. So pay attention to gases becoming gases. Look back in topic 3. But that's what you should be discussing for B. Gases becoming gases, and how does entropy affect gases becoming gases? Because the entropy does increase and decrease. This is not, some people say it stays the same because it's a gas becoming a gas. But please go back into your notes for that one. That's what you need to think about for B. For C, what is the sign of free energy at 298 Kelvin? Guess what, guys? This 298 Kelvin wasn't necessary. It doesn't even matter. But the reason it's here is because it's saying this reaction happened at this temperature. It's kind of like it's just there. But you don't need this number for anything. The question for this one is, it's kind of basic. So what's the sign? So we say at 293, it says that the reaction above proceeds spontaneously from standard conditions at 293. So what's the sign for free energy? The answer to this one, if you're not sure, review what delta G is, what is free energy, because the answer to this one is actually in this question here. This question answers it, but you need to understand what free energy is. And for the last one, what is the sign for change in enthalpy? What's the sign for the change in enthalpy? Well, to figure this one out, I would like you to kind of work with what you know. From C, you should know the sign of free energy. And from A, you should know the sign for entropy. If you use your equation, you can answer this question. And the equation is that free energy equals, let's see here. Your equation is free energy equals enthalpy minus temperature times entropy. So using this equation here, we should be able to figure out what this sign is, because you know this sign and you know this sign, and you also know temperature. Since it's in Kelvin, it's always positive. So the Kelvin's not going to change anything here. So what I say you should do for D, if you still haven't figured it out, or what you should have written if you did figure it out, you should talk about this formula to get here. And to solve, the best way to do this is to solve for delta H. Delta H, what would that equal? Well, if I add, and I'm going to take out this temperature because it's always positive, and so we're really talking about if we know the delta G and we know the delta S. So to move the delta S to this side, it's negative, I'd have to add. So it's delta G plus delta S. And since we know if delta G is positive or negative from one step, and we know delta S is either positive or negative from another step, because we know if we put in arbitrary positive, negative, whatever's appropriate here, and positive, negative is appropriate here, and add them together, we should be able to make some sort of conclusion on what delta H is. In your explanation, making an equation or something like that will be a lot easier to explain. It's a lot harder to explain an equation than to write an equation in your answer. So I highly recommend that you do something like that. I will be checking your essays, and wish you luck, but before they're due, make sure you ask questions. Ask me questions, ask other student questions, but hopefully my little tutorial here, or a little explanation, little hints, made you a little more confident in your answers, or let you know like what you should be thinking about in your answers. But please go back in the lessons and double check your work. I will talk to you soon. Have a good one.